Hey everyone, this is Mrs. Harding. Welcome back from spring break. Today we're going to start chapter 11, which will be a little bit of a change of pace. We're going to be talking about something called the chi-square goodness of fit test. And we're going to go through all the parts of any significance test. If you take a look at the learning targets for chapter 11, we're going to be stating the hypotheses, a null and alternate hypothesis for the chi-square goodness of fit test. We're going to be going through some conditions that must be met before the test. We're going to talk about degrees of freedom and p-value for this test. We're going to perform the test and then discuss an analysis at the end. So if you go to your OneNote notebook and click on activity 11.1, we'll get started. So the example there is about zodiac sign and success. Does your zodiac sign determine how successful you will be later in life? Fortune magazine collected the zodiac signs of 256 CEOs of the largest 400 companies. The table shows the number of births for each of the 12 signs. You can find yourself in there. Now, if you look at this is a whole distribution of categorical data. So we're not analyzing one proportion. We're not analyzing the average of data collected. We're looking at a distribution of data over many categories. You can see from the table there's variation in the number of births per sign and that there are more Pisces. But is this enough to claim that successful people are more likely to be born under a particular sign? Well, think about what you would expect. There's 12 signs there. Out of 256 people, you would expect about 21.3 people or CEOs born under each sign. That would be the expected count for each of those categories. So then the question is, how well does this data fit what we would expect, that model of 1/12 of the CEOs being born in every month? And this is what we're going to address when we talk about the chi-square goodness of fit test. How well does something fit the distribution that we would expect? So if you flip to the next page, we can get started with what this test actually looks like. In the table, we have the counts of 256 CEOs distributed among the 12 zodiac sign categories. And you can see counts is in italics there because I want to emphasize here that we are actually talking about how many of the items fell in each category. We are not talking about a proportion. We're actually talking about the counts. So then let's go through and look at what the null and alternate hypotheses would be. For this type of significance test, your null and alternate hypothesis are most often written in words. So you can see the null hypothesis, births of CEOs are uniformly distributed over the 12 zodiac signs. The alternate is just that they are not uniformly distributed. So what's the population? Remember, this is always an important piece. CEOs of the largest 400 companies. What parameter are we interested in? What proportion of all CEOs are born under each of the zodiac signs? Okay, so the next step after you've stated the null and alternate hypothesis is to go through the conditions. The first condition always is randomness. Is this a random sample? And you can see there what it says on the screen. It's not actually clearly stated whether this is a random sample or not. The second condition sort of goes along with the third condition. There's not really any need to write down the second condition, but it's something that you need to make sure you have. And it's that you actually have counts for each of the categories. We want to pay attention to this. Sometimes you're given the actual count, sometimes you're just given proportions or percentages. Make sure that you do actually have the count. So in this situation, there are 12 categories, and we do have the counts for all of them. And then the third condition that you do need to write down, the third condition is that all of the expected counts are at least 5. As always, having larger sample values, larger number of sample values is typically better. So we need to have at least 5 in every category. You can see here 21.3 is definitely over 5. So we've met this condition of all of the counts being at least 5. The fourth condition is independence. This is the 10% condition. So we've done sampling without replacement. However, this one is actually violated. 256 is more than half of 400. So we have sampled more than 10% of our stated population. So this condition also is violated. So in this situation here, we don't clearly have randomness met, and the 10% is definitely violated. But as always, once you've commented on the conditions, you're still going to proceed with the test even if they're not satisfied. And what we're going to look at, the distribution for the goodness of fit test doesn't follow any of the previous distributions that we've encountered so far. The new distribution is called the chi-square distribution. So that's what we're going to take a look at. Go ahead and scroll to the next page. Let's look at what a chi-distribution actually looks like. It says the chi-square distribution is a family of density curves that takes on values that are greater than or equal to 0 and are mostly skewed to the right, but approach normality as the degrees of freedom increases. So this is like the t-distribution, and that the shape of the distribution varies according to its degrees of freedom. The characteristics for it, the total area under the curve is 1. Each chi-square curve begins at 0, reaches a peak, and then becomes asymptotic to the horizontal axis. Each chi-square curve is skewed to the right. There are some examples down here. As the number of degrees of freedom increase, the curve begins to look more normal. So you can see here degrees of freedom of 1, degrees of freedom of 4. The peak is moving further to the right. Degrees of freedom is equal to 8. Here you can see that they approach the horizontal axis. And how do we figure out these degrees of freedom for a chi-square? The degrees of freedom is 1 less than the number of categories. So in that last example that we had with the 12 zodiac signs, we would be talking about a degrees of freedom of 11. What we would use this distribution then for is to calculate the p-value. The p-value is always the area under the chi-square curve to the right of the test statistic. And that will probably make more sense to you when we actually calculate the test statistic. It involves squaring, and numbers are always positive. So we're always looking to the right of the test statistic. So then if you scroll to the next page, let's talk about how to actually calculate the test statistic so that you can determine the p-value. Here's the formula for the test statistic, and these are always in counts. So make sure you're thinking counts, not proportions. It's the observed count minus the expected count squared over the expected count. You do that for every single category, and then you sum them up. So in here, in the CEO zodiac problem, the observed counts are the number of births that actually occurred under each sign. The expected counts are what we determine, the 21.3 for each month. So in this table, it lays out all of the values. I'm only scrolling so far because I want you to fill some of these things in. So for an Aries, there were 23 that were observed, 23 CEOs that fell under that sign. Again, we expect 21.3. So then following this formula, observed minus expected squared over expected, you get a value of 0.130. Now, if you were to do this again for a Taurus, the observed is 20, expected 21.3. Following the formula, get 0.083. Now, why don't you go ahead and pause the video and fill in those values that are not already filled in. Okay, so you should have determined those values that you see in the table. The final piece of calculating the chi-square test statistic is to sum them all up. So the test statistic for this distribution is 5.094. To find the p-value, remember we need to know the degrees of freedom, so the degrees of freedom are 11. So let's go to your calculator to determine that p-value. You want to go to second, variables. If you look down at option 8, it's chi-squared CDF. You're going to put in your test statistic up to a very large number, and then your degrees of freedom. And you can see that you come up with a p-value of 0.9265. Now at this point we need to interpret this value. You can see that the p-value is quite large, so we're going to fail to reject it. There's little evidence to suggest the distribution of births among CEOs of the top 400 companies is not uniform. If the distribution of CEO births is uniform among the zodiac signs, then the chance of getting counts as or more extreme than what we did is 0.9265, which is actually a very large percent. There is also a table C in which you can come up with a range for the p-value, but for this particular one, if you look at degrees of freedom of 11, there's no entry in the table that would correspond to 5.094. The first value is 13.7, which gives you that p-value of 0.25. You can do this last one on your own to verify your calculator and the table. So let's take a look just at the summary. It says, suppose the counts, random, large sample size, and independent conditions are met. So let's review what those were. Counts just means we have the counts. You don't actually have to write that one down. But we need to be sure that it was random selection. The large sample size means that the expected counts in each category is at least 5. And the independent condition means if we are sampling without replacement, we cannot sample more than 10% of the population. So if those are met, then our null hypothesis is that the specified distribution of the categorical variable is correct. When they say specified, it could be the expected or what you would assume it to be or what the claim is from a company. And then the alternate is that the specified distribution of the categorical variable is not correct. You can also write them with values, but it's not necessary. When you go through the test, so you've gone through the conditions, stated the hypotheses, to actually do the test, you need to make sure that you have the expected counts, and then you're going to calculate the chi-square test statistic according to the formula. You're going to then find the area to the right on that chi-square distribution with k minus 1 degrees of freedom, where k is the number of categories that you have. And then here at the bottom, it just restates those conditions again. As with all of our significance tests, you can do these in the graphing calculator also. What you're going to want to do is put your counts into list 1, your observed counts in list 1, and your expected count into list 2. And then from your list of tests, remember you hit stat, arrow over to tests. You're going to select the chi-square goodness of fit test so you can see the screen that's shown there. You put down your lists and your degrees of freedom. And then you can choose to either calculate or draw. And you can see the differences in the bottom. The one on the right is the shaded area to the right of our test statistic. Remember, it was quite large, 0.9265. On the left, the calculated screen gives you the p-value also. It gives you the test statistic right here. And this piece right here is something of interest when it comes to an analysis about your test. These numbers right here are the individual terms that you would have calculated if you had been doing this by hand. So like this first number is the individual term that might correspond to what, I've already forgotten what the first sign is. Is it Aries? And then the second one is the second category, and the third one, the third category, and so on. You can right arrow through that list. If you need to see that list, you're going to want to right arrow right away. If you hit enter or other buttons, you may not be able to scroll. But why is that important? In your analysis or in your conclusions, it's also typically good to comment on the terms that are contributing the most. So in here, you'll see some that are very large compared to others, and those are the ones that are contributing the most to the chi-square test statistic. You can arrow through all 12 and see which ones are the largest in there. On this next page, I would like you to go through this problem. So pause your video, give this problem a shot, and then come back to the video to check your answers. So one of the first tasks on this problem is just understanding this chart that they're giving you, because these are the counts that you would expect. And so they go through and talk you through it to show that they would suspect there would be 9 red-eyed straight-winged, 3 red-eyed curly-winged, 3 white-eyed straight-winged, 1 white-eyed curly-winged offspring. So these are going to be your expected counts for this significance test. So if we're carrying out this test at the significance level of 0.01, we need to make sure that we do have all of our values here. You have the observed values as they were listed in the question. And based on those proportions that we just showed, out of 200, this is how many you would expect to have those characteristics. You should go through the conditions. We do have the counts. The offspring are from random mates. All of them are at least 5. And 200 is easily less than 10% of fruit flies, sadly. The null and alternate hypothesis, the null is that the proportion of fruit flies within the population of offspring will be in the ratio 9 to 3 to 3 to 1. The alternate is that they will not be in that ratio, and you don't have to get any more mathematical than that. All right, then conducting the calculations. This is following the formula observed minus expected squared divided by the expected, and then summing them all up. So you get a chi-squared test statistic of 6.19. There's a lot of space on that page. There were 4 different categories, so our degrees of freedom is 3. And you can go to your calculator and do a chi-square CDF to get the p-value of 0.1029. So at the 0.01 significance level, this is not enough evidence to reject. So we failed to reject the null hypothesis. There is not sufficient evidence to suggest the fruit fly offspring with the various traits will not be in the ratio 9 to 3 to 3 to 1. Now remember, we're never proving the null hypothesis is true, so we're not saying that it's definitively true. We're just saying that this particular sample did not give us evidence to disprove it. This brings us to the end of activity 11.1. So for your homework tonight, you are doing the assignment that you will find on Canvas. Just to kind of recap the learning targets here, this is the only activity for 11.1, so we have covered all of these things. Stating the hypotheses and computing the expected counts for a chi-square test of goodness of fit. Checking the conditions, random selection, 10%, large counts. Knowing how to find the degrees of freedom, which is always 1 less than the number of categories, and finding the p-value. Performing an entire test, all parts. And then discussing or analyzing at the end in terms of which category is contributing the most to your chi-square test statistic. As always, if you have any questions, please let Mr. Bowman or I know. Enjoy the rest of your day.